Okay, picking back up with the slope fields, we're looking at example number 4, and our last video we just ran out of time, but we're looking at a slope field. What you're going to really do here is make a quick sketch of what tangent line slopes would look like at individual ordered pairs. So, for example, as I'm looking at dy dx, which is the tangent line slope, if that's equal to the cosine of x, let's consider what would happen if x is equal to 0. If x is equal to 0, and of course, regardless of what y coordinate I'd be plugging in for a given ordered pair, that wouldn't matter. If x is equal to 0, you could quickly see that dy dx is the cosine of 0, and the cosine of 0 is actually 1. So what I'm going to do is I'm going to come over here and make some quick sketches that whenever we have x equals 0, regardless of which ordered pair we're working with, the cosine at that ordered pair is going to give you a value of 1. And I'm not drawing a full tangent line, I'm just drawing a little short segment here. You can think real quickly, what if x is equal to pi over 2? Well, if x is equal to pi over 2, there are infinitely many points that would have an x value of pi over 2. But dy dx, the cosine of pi over 2, cosine of pi over 2 is 0. So wherever we would have an x value of pi over 2, and you can see they're giving you little points here, and they're asking you more or less to just give a quick kind of a sketch as to what that tangent line slope would look like. What about at pi? Well, if x was pi, cosine of pi is -1. dy dx would have -1. Well, again, what you can see more or less is, again, you've got infinitely many ordered pairs that you could be looking at. But that, of course, would be a pretty good sketch. Finally, what about 3 pi over 2, at least for positive values here? If x was equal to 3 pi over 2, cosine of 3 pi over 2 is 0. So once again, we'd be at dy dx is equal to 0. So we'd get some information as to what tangent line slopes might look like. Again, we can think, what about these negative values? At negative pi over 2, cosine of negative pi over 2, well, again, dy dx would be 0. Same thing with negative 3 pi over 2, which would be coterminal with pi over 2. You can see we've got a horizontal tangent line slope. And what about at negative pi? Well, on the unit circle, negative pi would be coterminal with positive pi. So if we were plugging in negative pi, dy dx cosine negative pi would actually equal -1. So we have negative tangent line slopes that would look like so. Now right now this might look like what you can see on the weather portion of the news is you might see some wind direction fields being broadcast up on the screen. And by the way, that's not a bad analogy as to what can be happening as you will continue to study differential equations in the sciences. But you might wonder, what value is a little sketch like this? Not that it's all that difficult to make. Let's just say that we wanted to solve this differential equation real quickly. We have dy is equal to the cosine of x dx. We could very quickly see that y would equal the sine of x if we took an antiderivative plus c. And the most basic constant that we could ever have would be 0. Now, what would that look like if we had the sine of x as a particular solution to this differential equation? You can see that an initial value, if I were to let x equal 0, the sine of 0 would be 0. Well, look, if I were to say this is a point that I'd like to have, look how the slope field can trace out what a solution could look like. These directions, this tangent line slope, look, would be increasing with the slope of 1 till we got over to pi over 2. It would flatten out. We can see we're going to have to come back down. Look, going to the left of 0 here, we'd be going in a manner like so. Look at this. The tangent line slopes begin to give us a little snapshot as to what an equation could look like that would be a solution here. So slope fields do have their value, and we do use them quite a bit. They show up a lot on AP exams, or at least they have in the past. Let's take a look at some matching for number 5. Use slope analysis to match each of the following differential equations with one of the slope fields. Don't use your graphing calculator. By the way, the fact that you're told not to use your graphing calculator, I am going to get you a program that can sketch these out. We'll talk more about that later. But I do want to say this much, that very often what can come into play, and it's not helpful as much here, is something called quadrant analysis. This particular problem that we have, the 5, or the 4, I should say, graphs that were given right here, quadrant analysis doesn't really help us as much here, but I do want to talk about it because it's a very useful strategy. Quadrant analysis is more or less saying, look, in the quadrants, in quadrant 1, x is positive, y is positive. In the second quadrant, we'd have x is negative and y is positive. In the third quadrant, we'd have x is negative and y is negative. And finally, in the fourth quadrant, you can see more or less that x would be positive, but y would be negative. And that, of course, can be helpful at times if you're doing some matching. Here's how. Let's take a look at maybe number 2 here, where we have tangent line slopes are going to be of the form of an x-coordinate times a y-coordinate, x times y. Well, we can think about it this way. In the first quadrant, x and y would both be positive. So we could look through all these choices and say, well, look, positive x values times positive y values should get something positive. Every slope in the first quadrant should be positive. Now, if I were to just look through the A, B, C, and D, I can see that answer choice B actually has some negative slopes. So I can tell you immediately that the slope field for number 2 cannot be answer choice B. And we know that, of course, because that first quadrant must have all positive slopes for that differential equation. You're seeing something negative there. Sadly, as we look in the other quadrants, though, you can't really narrow it down. Obviously, if you had x comma y here, x comma y, the second quadrant should be negative because you have a negative x value and a positive y value. It looks like the remaining possible answer choices of A, C, and D all have negative tangent line slopes. Similarly, in the third quadrant, looking at number 2 here, if x is negative and if y is negative, multiply them together, you should have all positive tangent line slopes. And again, ruling out B, we knew B couldn't be it. C, D, and A all seem to be quite realistic. They seem to be quite possible. And same thing with answer choice with the fourth quadrant coming into play. If x is positive and y is negative, that fourth quadrant should have all negative tangent line slopes. That's more or less what we're seeing. So quadrant analysis sometimes will help you identify things very quickly. In this case, at the very least, it's ruled one of these out. Let's continue to talk about number 2. Maybe just since we started there with some quadrant analysis, you might think, what do you do if perhaps now you don't know where to go next? Let's just maybe fix something in here. Let's let x equal a fixed value of perhaps 1. Okay, and it very well could be other values. If that's the case, then dy dx would be really just 1 times y. It would be completely based on its y coordinate. So that the higher we go on that x equals 1 vertical line, the higher we'd go there, we'd expect to have larger tangent line slopes. For example, if I looked at the point 1 comma 10, where my x was 1 and my y was 10, we'd expect our tangent line slope then to be just a 10. The higher up we go, the further we get away from the x-axis, the bigger the slope would be. You look at A, and that's not the case. You can see what's happening. This tangent line slope looks like it's getting smaller. It's getting flatter the higher up we go. So we know that it couldn't be A. And then perhaps we're looking at what's happening in this situation with C and D. You could think, well, my goodness, as I'm looking here, it looks like they're kind of similar. And that can also beg the question, where do we go next? You could say, well, what would happen if x equaled 0? If x equaled 0, 0 times y would always be a 0. We would expect this to actually always have a horizontal tangent line slope of 0 when x equaled 0. That would be answer choice D. It sure looks like D would be the most likely answer. For C, it looks like these are vertical tangents, meaning we're approaching infinity. But that's just a process of picking out a correct one. With this in mind, we can immediately jump over to 3 and 4 and wonder if perhaps this could help us out. If we know that D is going to be the case, and by the way, you could do also for number 2, you could let x equal -1 and so forth, and look at what's happening in some of these other situations. But let's take a look at, say, number 3. dy dx is x all over y. At this point, we might wonder, what's happening as, x would equal, say, a 1. If x was equal to 1, dy dx would be 1 over y. It's the reciprocal of y. And that means the larger y is, the smaller our slope would become. So we might wonder what's happening, say, at C. You can see the higher we're going up here, it looks like the steeper we're getting. We think that it's not going to be C. We already ruled out a D. With B, if x is equal to 1, we wouldn't expect for there to be a negative tangent line slope. Looks like we can pretty much say that it's going to have to be A. The higher up we're moving, it looks like we're flattening out. You can see what happens when x equals -1. We'd have a negative tangent line slope. If x equaled 0, 0 over y would just be a 0 itself, and we're getting that for A as well. So now we're down to a process of elimination with, for number 4, y over x looks amazingly close to what we had for number 3. Obviously you interchange the numerator and the denominator. If x were to equal 0, I think you can quickly see that when you divide by 0, dividing by something very small, you get something very large. It sure looks like C would be the most likely possibility for that to happen. We should double check what's happening if, say, x is equal to 1. If x would equal 1, your dy dx would simply be what your y coordinate would be. The farther away you go, the higher up on this, the larger your y coordinate would be, and so forth. It sure looks like C is fitting. By process of elimination, it looks like number 1 would have to be B. You could, in fact, double check what's happening here. You could let x equal 0 and see that dy dx would be the opposite of y. And you can more or less confirm that 1 would link into B very well. So quadrant analysis, letting x and y equal 0, letting x equal 1, and doing some slope analysis, those are all valuable things. Let's move on to the last part of this video, which is Euler's method. Sometimes you won't have a direct particular solution to a differential equation. You very well can still get an estimate for what's happening on the curve. using a method with tangent lines, something called Euler's method. This is a definite AP exam problem. It's a traditional problem